Hello and welcome to Ask Echometer. My name is Carrie Ann Taylor, and along with myself from Echometer today we have Gustavo Fernandez, who always does a great job running the chat in our Q&A session. Also Ken Skinner, Tony Podio, Dieter Becker, and Lynn Rowland, who will be presenting today. And this is our 20th session. Can you guys believe it? 5 months of sharing our Wednesdays with you, and we have truly enjoyed it. We really appreciate you all joining us. You are what makes this so much fun for us. So we have an Ask Echometer webpage that's accessible from our echometer.com website, and you can go there right now if you'd like and download the Session 20 PDF documentation bundle. And that contains a PDF of today's presentation, as well as 4 technical papers, 3 Excel spreadsheets that are referenced in today's session, and then right next to that PDF bundle link is a link to download the TAM and QRod examples that Lynn is going to use today. If you don't already have the QRod 3.1 software installed, there's a link for that too, right next to the examples link. And also, if you don't already have the TAM 1.7 software installed on your computer, you can download it from the software page, and there's a link directly from the home page to that TAM 1.7 download. Today's session is titled Sucker Rod Pumping System Design. We're using QRod 3.1. So Lynn, I will turn it over to you now.
Thank you, Carrie Ann. This program called QRod, the term QRod stands for Quick Rod Design. And the program came from, this is a reference right here, from Dr. Jim Jennings, petroleum professor from Texas A&M. And Echometer acquired the software from Dr. Jennings back in 1994. And we've been donating it to the industry free of charge. It's sort of an ad-based software, supported software, because we advertise Echometer, but it's free of charge to use. It's the most widely used sucker rod design program in the world. Maybe because it's free, but also because it's very accurate. The paper here that's referenced 2015, Norm Hine, myself, and Scott Malone, we wrote, we compared the different design programs that were on the market, QRod to the other 2 that you paid money for, compared it to the surface measured horseshoe load cell data on 6 wells, and QRod matched the best of all of them. We also have a couple of papers here. This one paper we published in 2012 is on slippage. QRod has a slippage equation that we'll talk about, and we've added some new tools, and we'll talk about those tools. So if you have questions, you're free to contact any of us by email. And again, Carrie Ann said the bundle is posted to download. There's QRod data examples, and those are export files from QRod. There's a couple of TAM examples, and then there's some Excel spreadsheets and PDFs. These papers are there. So QRod is a very simple to use, user-friendly design program. It has a damped wave equation in it, one-dimensional damped wave equation. So it's state-of-the-art. You can use it to design and predict the performance of your sucker rod equipment. It predicts the surface loads, utility stroke length. It predicts the plunger velocity and the pump stroke. And so that's what predictions are. And we use it to calculate the torque on the gearbox. We also use it to size the motor. And it's really easy to make, and again, design the rod string. It's easy to make changes of tubing anchor, stroke length, strokes per minute, pump depth, plunger diameter, and instantly see the change. And you can size based on flow rate or strokes per minute. Either one will work. And then this last change we made in 2015, we added the system of units, any systems of units. So people anywhere in the world can use the software and display their calculations in their units versus U.S. Units. This is a TAM example, and this is a surface card and pump card. And this data was acquired at the surface while a downhole load cell was run in the well back in 1996. And this well has measured loads with a horseshoe load cell, and QRod, when we use QRod to calculate these conditions, QRod matched these conditions the best. Even though the pump wasn't full, QRod had the best match on the loads. So the surface dynamometer card is a plot of the load versus the stroke, upstroke and downstroke. So here's the upstroke and there's the downstroke, and QRod is used to predict that. And in TAM, we measure this data and we use the wave equation to predict what the loads and position are at the end of the rod string. So we call QRod a predictive program, and we call TAM and T2M a diagnostic program. So when you have a predictive program, you input something like pump intake pressure and surface stroke length, and then the program and the rod string that you want to use, and then QRod will calculate or predict the surface loading based on the properties of the rod string and the tubing fluid gradient and things like that. And then it uses a plunger size to predict the load at the pump, and then we calculate the downhole stroke. And we can do either anchor to unanchor tubing, wherein the measured diagnostic software like TAM and T2M, we measure the surface loads on the upstroke versus stroke, and on the downstroke we measure the loads on the downstroke, and that we call that is a acquired or measured surface dynamometer card. And then we use a wave equation to calculate the effect of the dynamic motion down the rod string with the properties of rods. And when we get to the end of the rod string, what's left over at the end of the rod string, we call that the pump card, and that's what is acting at the bottom of the rod string. Now, when you look at this, you see that the peak load here matches really close, and that's because we match the fluid load very close on the upstroke. But this is a plot from the T2M software, and notice that here the pump card load goes below zero. Well, this is in T2M we had the same damping factor on the upstroke and downstroke, whereas in QRod we only have one damping factor the same on the upstroke and downstroke. But in actuality, this example shows there's additional mechanical friction on the downstroke that if we'd rented this in TAM, we would have taken some of this away, and the pump card would have been closer to zero and matched more of the ideal condition. But QRod eventually someday will have an upstroke and a downstroke damping factor, but now we just have one. So this is the beam pumping simulator that we're trying to show what QRod calculates. And so based on the pump unit type, we specify the type: conventional, clockwise or counterclockwise mark, or air balance pump unit, and that defines the motion, the kinematic motion of the pump unit, and it's a generic motion, and we base that motion based on the stroke length and the type of pump unit, and that inputs the motion at the surface, and then we input the type of rod string, and then the tubing fluid gradient, and we also put in the plunger diameter and the true vertical pump depth, and then the wave equation then simulates this motion through the rod string down to the end of the rods, and at the bottom of the rod we have the pump load, which is we input the plunger diameter, and we input the tubing intake pressure, and we input the tubing pressure, and that allows us to calculate the pump load, and the wave equation then calculates the downhole pump stroke. And once we've solved those surface loads and the pump stroke and loads and the plunger velocity, then we also calculate a synthetic torque curve based on the type of pump unit and the rod torque, and then we determine how many weights that are needed, the counterbalance, and the counterbalance effect load. And so you can use that to position your weights on the pump unit. And so this is an output from QRod. And QRod is simple, so it only assumes that the pump is filled with liquid. And so these cards, pump cards, are full of liquid. And this is anchored tubing and this is unanchored tubing. And so we calculate the effects of a full pump. The pump's working properly, there's no gas in the pump, and we calculate the surface loads based on either anchored or unanchored tubing. Now, when you talk about the slope of the surface card, this line right here represents, what this represents is the stretch of the rods. And so as the load goes up, then the surface load, the pumping unit stroke moves up. So this is moving up and increasing load, moving up and increasing load. And the slope of this line is the rod stretching to pick up this fluid load. And so this is what we call, this is a rod string. When it's this slope is the rod string acting like a giant spring. And so here it's stretching to pick up the rod loading, and here it's unstretching to pick up the rod loading. And it has this peak load because it has to accelerate the surface to apply the pump load at the end of the rods. And then this minimum load is created by it, again, pumping faster than 0 strokes per minute. It accelerates moving and creates this minimum load. And so this is the minimum load and the peak load, and the slope is determined by the stretch of the rod string if the tubing is anchored. Now if it's unanchored, we see the tubing pump card lean over based on the motion of the plunger with respect to the barrel, because the tubing is releasing the load onto the rods and it's unstretching, and that causes a plunger to move with respect to the barrel, and we get this movement. And also you'll see that the surface card leans over more, because in the surface we see both the unstretch of the tubing and the stretch of the rods. So when you use a predictive program like QRod, you can see if your pump unit is operating as you expect. You can compare it to the measured data. You can see how close it matches, and we've modified QRod in this last release in 2015 to allow you to import a dyne file exported from measured data, so you can overlay measured data on top of predicted data inside QRod, and we'll show that later. And if it doesn't match up, you can modify change the speed, or change different equipment in the well, change the stroke length, change different things until you can get a match, even change the damping factor, change the intake pressure. So all those things can be changed to try to get a better match of the equipment. Now, this is a simple example here, and we're going to run QRod and assume that the well is 5,000 foot deep and the stroke length is 100 inches, and the tubing pressure is 50. I may make it 80, I can't remember. 50, and the intake pressure is 50, and it's a 2-inch pump, 2-inch diameter pump, and it's anchored tubing, so there's no tubing movement. And the fluid load calculated based on a tubing fluid gradient of water, fresh water, is the height of the pump card should be 6,896 pounds. And the rod string is a 7/6 API rod taper, and we'll talk about that in just a minute. What does 7/6 mean? Well, I've had people call me and say, how do I put more than 76 rods in QRod? Well, it's not 76 rods. It's the 7 is the top diameter in 7/8 of an inch, and the 6 is the bottom diameter in 1/8 of an inch. So 7/8 and 6/8 are 3/4 on bottom. So it's API rod taper designation. So when you run this rod string in the well, QRod will calculate there's 41% 7/8 and 58.8% 3/4 rods in the taper. The larger rods are at the surface and the smaller rods are at the bottom. And the rods weigh in this 0.433 tubing fluid gradient fluid 8,288 pounds. And the rod string, based on these lengths, is a giant spring, and if you could walk up to that rod string, you pull on it with a force of 254 pounds, then that rod string, if it's anchored at the bottom, will stretch exactly 1 inch. So this is the spring constant for the rod string, and the rod string moves up and down 100 inches at the surface. So if you were to stick the pump and move the rod string up 100 inches, then the entire pump stroke would be lost because it would be stuck. And you take 100 times 254, and that'd be 25,400 pounds required to stretch the rod string equal to the stroke length. That's what we call SKR, the stroke length times the spring constant. Now, we're not going to put 25,400 pounds on the rod string, but we're going to put the fluid load on the rod string. And so the fluid load is a fraction of this total fluid load, this load right here to stretch the entire rod string, the surface stroke length. So if you take 8,288 pounds divided by 25,400 pounds, then that means that that ratio is 27%. What does that mean? That means that 27% of the surface stroke will be lost to stretch to pick up the fluid load. And so that's what FO over SKR is. So you're stuck with that. Whatever the fluid load is and your rod string spring constant is, that's how much of your surface stroke length you lose to stretch. Now, we'll get some of that back due to over travel. So here's a table that, for people who don't like fractions, if someone says I've got an 8/6 rod string, that means I've got 1-inch rods on top, that's 8/8, and 7/8 rods in the middle, and 3/4 rods on bottom. That's called a 8/6 taper. The 7/6 taper, which is common in 2 and 3-inch tubing, would be 7/8 rods on top and 3/4 rods on bottom. The biggest taper QRod supports is a 10/9, which is 10/8 on top, 1.25 rods on top, and 1.1 rods on bottom. So it's called an API rod taper number. Okay. So when you see this number, it means a designation of the rod string. Now this is the output from QRod, and you have 3 graphs on the right. We have the surface and pump card at the top. We have the plunger velocity in the middle, and we have the net torque curve at the very bottom. And so when you these are the design inputs, and I'm going to blow them up so you can see them more clearly. You drop this down, this little arrow down, to pick the type of pumping unit, and there's 4 different types we'll talk about later. You type in or drop down the depth. You can just type in a number, or you can drop it down, drop down a list. So it's easy and quick if you just select off a list. You can also just type numbers in. It works just the same. Here's your surface stroke in inches, and these little drop downs here let you select the units. If you don't like feet in inches, you can change it to be other units, like probably newtons or pascals or whatever, and meters or centimeters. And here's the plunger diameter, and the tubing size is in a table, and so we have 2 and 7/8 tubing as well, and it's anchored, so there's no stretch. If you check that box, that means this line is going to be vertical, and that means that the rods are going to stretch to pick up the fluid load, and the pump won't move until the fluid load gets picked up. And with that corner right there, when the pump load gets picked up, that means the standing valve opens, and then the plunger can move on the upstroke. You can have steel or fiberglass rods in the well. If you put in steel, steel is going to use this API taper. You can select the grade of rods, fairly simple. If you go here at the bottom, there's some default settings, and we zoom in here. There's little calculators that we've added. You can calculate the sinker bar weight. We'll talk about that. You can calculate the tubing fluid gradient, which is dependent on the oil and the water production rate. You can calculate the plunger clearances, and that lets you calculate your volumetric efficiency of your pump displacement by losing your total pump displacement. We subtract out the slippage. And we have tubing pressure here is 80, casing pressure is 45, damping factor is just 1 damping factor, up and down are the same. And then the surface efficiency of the pumping unit is 95%, and that's used to calculate the motor size. A big unit, more than about probably a 128 or 256 is going to be 95% efficient, so it's massive. A small unit that's less than 128 gearbox and rating is probably 80–85% efficient. It's not as efficient, and so you may need a larger motor. So what that means. Here you can specify the pump intake pressure, which I usually use, or here you can put in a PI curve and let it calculate the pump intake pressure as a function of the production rate. And it uses a PI straight line drawdown to relate pump intake pressure to production. So here's how you adjust your pumping speed. If you click on this, you can change each click creates an increase or decrease of the strokes per minute. If you don't want to input strokes per minute, you can click on this button and click on enter a pump displacement as target rate, and when you click calculate, it'll iterate until it finds the speed for that target rate, or it's just going to use that speed to calculate the pump displacement. Now this is your results, pretty simplistic here, and so the results in this case would be 174 barrels of pump displacement with 5% slippage, and there's your rod string design. 41.2% is a 7/8, and 58.8% is a 3/4. The loading based on modified Goodman is 81.7% of the modified Goodman stress range rating. This is your maximum gearbox side required to meet your net torque loading and your structure loading. There's your structure of your loading. That number right there comes from the peak polished rod load, and that's the stroke length that you typed in. So there's your API. I guess it's minimum API pumping unit size. This is your motor size. NEMA D motor size is 10.7. You probably can't buy a 10.7, so you probably buy a 12.5 or 15 horsepower motor. There's your polish rod horsepower, the work being done at the polish rod. There's your weighted rods and fluid plus your fluid load, and then there's your weighted rods and fluid calculation there. So that's the results, and all this will be printed into a one-page PDF report. Here's your net torque on your gearbox. It calculates a balanced peak torque, and the peak torque here is 335,000 inch-pounds. That's just a little bit above a 320 gearbox. Counterbalance moment to balance the torque on the gearbox. Rod loading is 700,000 inch-pounds, and so that determines how many weights you'll need to place on the crank, along with the crank counterbalance moment. And then this is your counterbalance effect load, and that tells you where your weights need to be placed to balance the pump unit. This is your surface card and pump card that are predicted. Again, we predicted the loads. So the peak load predicted was 17,000. Minimum load was 6,496. The pump load calculated from the input data, plunger size, is 6,895 pounds. The pump stroke length is the total net pump stroke length is, assuming the tubing is anchored, is 74.57 inches. The stretch is 27.1% of the surface 100-inch stroke, so you lose 27 inches. But since we're pumping faster than 0 strokes a minute, so this is 5 strokes a minute, we get over travel of about 1.7 inches. This F over SKR is the percent of stroke that you lost to stretch. And then KR is your spring constant for your rods, and KT is your spring constant for your tubing. And then there's your report, and then there's a plunger velocity plot also. And what I'm showing here is I'm just going through and clicking on this little button, and as soon as I click on it, it increases the speed by a tenth of a stroke per second. And it's recalculating all the numbers and results on the screen. It's recalculating the velocity plots. You can see right there that the plunger velocity drops to 0 right there. You can see a little drop in the load right there when the plunger velocity goes to 0. You should get net torque calculations. And I guess my point is that it's a really simple, quick, easy use of program. There's very minimal input, and it's really quick to make changes and recalculate and see the results of making a change. Now, this is an idea showing the data from, first of all, the blue is calculated by QRod, and we put in parameters to match measured data that was acquired with TWM in the past, and we assumed either the tubing was anchored or unanchored. And you see here that this little pinkish color here, I think that's called fuchsia. Usually I just call it ugly. But anyway, it doesn't match up very well. And so there's something wrong if we assume that the well has anchored tubing. And this well is only 3,000 foot, it's less than 3,000 foot deep, so it's common not to run a tubing anchor. But when we set the setting that it's unanchored, the surface data calculated, predicted, matches very close with the imported data from the dyne file that was measured on this well. So the software, the QRod software has a feature that allows you to import and overlay measured data with predicted data, and if all the inputs are correct, and the QRod matches very closely, usually with the measured data. This is the pumping unit selection, and so when you click on this little drop down here, you get clockwise conventional. Now, this is counterclockwise conventional. This is Mark II and air balance, and so those are the four kinematics you select. When you select the pumping unit, you select the linkage, and the linkage defines the motion of the crank with respect to the motion of the polish rod. And so that's what we're doing when we select this. We're defining how the pumping unit motion of the crank and the motion of the polish rod are related. Now, for those that haven't talked about clockwise and counterclockwise, when you view the pumping unit from the side, I'm viewing the pumping unit from the side. If I would have put my hand out and the polish rod was in my right hand, then this is clockwise rotation versus counterclockwise rotation. Some people like to say that the crank arm falls toward the wellhead when it's clockwise rotation. So when you click calculate on QRod calculates the gearbox rating in thousands of inch-pounds required for your prediction. It calculates the structure rating based on the maximum polish rod load from the predicted polish rod load. And it calculates the stroke length based on the stroke length that you typed in. And we call that the minimum pumping unit, API pumping unit size. So here I click calculate, and here is the minimum pumping unit size for this well, for these conditions. This well is the Texas Tech test well, and here is the net torque displayed here at the bottom. I've blown that up, and it shows us the peak torque. There's a peak torque right there. It shows us the moment required to balance the loads from the weights and the counterweights and the crank, and it shows us the counterbalance effect tells us where to put the weights on the crank. And so that's what we calculated inside QRod. Now, if you look at the average of the torque load, the average is this line right here. And when we talk about something called RMS includes the change. It's like the change. It's really the change in the torque. And so the way RMS is calculated is that you take a square of the actual value, and it makes these when you square negative numbers, they become positive. And so the farther the RMS is from the average, the more changing load or cyclic loads we have, and that ratio is called the cyclic load factor. So when you see a unit that's not matched to your rod loading, it's not matched very well, you tend to see more up and down changes in that torque, and that would tend to show a much higher cyclic load factor. So when we calculate the cyclic load factor, which is the RMS torque divided by the average torque, we use that to calculate the horsepower of the motor. And so you take the polish rod horsepower, which is the area of the surface dynamometer card, that's horsepower at the polish rod, times the cyclic load factor, divided by the unit efficiency. And so if you have a big unit, it's usually going to be 95%. unit efficiency. If it's a smaller unit, you're going to probably use a little bit bigger motor, would be 80%. And so that's how we typically calculate the size of electric motor. Now, when Bob Galt was a famous sucker rod pumping unit designer, and Bob Galt said, don't worry about this, just take the polished rod horsepower when the fluid level's deep and take it times 2, and that will give you the correct size of motor. But QRod uses this method. This is the method QRod uses to calculate the motor, the input motor size, the horsepower. So when you click calculate in the QRod, it's going to design you a NEMA motor, NEMA D motor. A NEMA D motor typically has from 18 to 13% slip. It acts like it's a much bigger motor to start, like 3 times bigger. It's got 275% starting torque. So even though it's a small motor, it has a big push to start up. And so when we click the calculate button, it says here we did a NEMA D, that's the minimum size, 10.4, probably pick 12.5 or 15 horsepower. I don't think you buy a 10.4 horsepower motor. The area of the surface dyno card is 5.9. The efficiency of this unit is 95%. And we're using the cyclic load factor from the ratio of the average torque divided into RMS torque to get the cyclic load factor. That's where that comes from. About 8 years ago, we put the help in QRod to be the manual. So when you click on help, there's a 20-page manual. Probably more than 20 pages now. We've added a little bit more to it. But the manual is included in the software. So if you download QRod and install on your computer, and you click help, then there's a text searchable manual, either in Spanish or in English, on your computer. Well, actually both on your computer. So under utilities, you can change the language to be Spanish if you want and save it. And then when you run QRod, it'll show all the reports and calculations and well, the numbers will still be the same numbers, but depends on the units. But it'll be either in Spanish or English, and you can choose whichever language you want to display it in. So this is in Spanish, and then the manual would be in Spanish, and then the reports would be in Spanish if you click Spanish as a language. And this is the English, and it's just a simple one-page report. So there's really a really condensed, simple one-page report from QRod. Now the calculators, each of them also have reports. So if you run a calculator, then that can then also print a separate report to your printer. These calculators that we've added are one to calculate the pump clearances, we call it a slippage calculator, and then one to calculate the length of the sinker bars to be used in your well, and it's basically a function of your depth and your tubing fluid gradient and your plunger diameter. And then the tubing fluid gravity calculator we've added, and before we just let you type it in, and it was 1 and people just left it 1, and that was an issue because you need to include the actual fluids in your tubing. Even if they're gas free, it's a better guess than just leaving it as 1. So to me, that was an important change we made to QRod the last time we made a change. And I said it's been 5 years, it's been 7 or 8 years now. And then we also put in the ability to import a dyne file and put the dyne file on top of a predicted surface dynamometer card, and we'll see that. And so here's the fluid gravity calculator, and you click on this little button, this little calculator, and then this screen pops open, and you can enter the oil gravity, the water cut, and the water specific gravity, and you can then it'll calculate the tubing fluid gradient, and then you can say use it in the calculations, and it will update that field right there when you say use, and then you can select any system of units you want to display the data in. So all these different units are available for tubing fluid gradient, and you choose what you want, and I think you can save that as a default. Now, why is tubing fluid gradient important? Because it has an impact on the weight of rods and fluid. It has an impact on the pump discharge pressure. It has an impact on the height of the pump card. So it's an important parameter, and it shouldn't just be defaulted to 1. So you should, enter your oil water cut, your oil gravity, your water gravity when you run QRod. So if you know the tubing pressure, and you know the true vertical pump depth, and you know the tubing fluid gradient that you've entered in, then we calculate the discharge pressure in QRod, and then we calculate, and you input the intake pressure, and then the fluid load, the height of the pump card, is the discharge pressure minus the intake pressure times the area of the pump, and you specify the plunger diameter. So you specify the intake pressure, the plunger diameter, and we calculate the pump discharge pressure from your inputs, and that's where the height of the pump card comes from, and that becomes the load that's applied to the end of the rod string during the upstroke for the predictive design program in the wave equation. Now, this shows the surface card and pump card versus a fluid level shot, and I'm showing the equivalent gas-free fluid here above the pump. And so QRod works off the pump intake pressure. And so when you look at the height of the gas-free fluid, that's equivalent, not exactly equal to, the pump intake pressure, because the pump intake pressure depends on the oil gravity, or the gravity of the fluid, and the tubing pressure, and the amount of gas above the liquid level. But when you think about the pump card, you see that the pump card, there's a maximum fluid load line. And so, in a diagnostic situation, when you shoot a fluid level, this distance here, the gas-free height, is how much lift is being provided by the well. And so the higher the fluid level, the smaller the pump card will be, because the pump intake pressure is going to increase and provide more lift. And so there's a relationship, and the height of the pump card is how far away the liquid level is, not exactly, but it's based on pump intake pressure. This distance here is equivalent to the height of the pump card. All right. Now, so I'm going to try to show that example. And here's an example I've already put on the web page that you can download, and it's called QRod Fluid Load, a function of pump intake pressure. And this case here is calculated based on a pump intake pressure of 50 psi. And so when you have low pump intake pressure, you have the most amount of your surface stroke length lost to stretch. You have the highest pump load. You have the highest peak load and the lowest minimum load. You have the most horsepower. Now, if you have a higher fluid level, notice that the pump stroke gets longer, because now the load is less, because we've raised this intake pressure and we've reduced the fluid load, and that means there's less stretch. So now you have a longer pump stroke, you have a lower peak load, you have less horsepower, and you have a higher minimum load. And if you raise the fluid level even more, you have even a longer stroke, shorter fluid load, less peak load, higher minimum load, less area, less work being done at the surface to lift the fluid to the surface. So let's just go back to real quick. Watch the pump stroke. With 500 psi, it's 80, and then 200 psi, it's 76, and then 50 psi, the pump stroke's now 74. So as you lower the fluid level, as you pump the well, you're going to have a shorter pump stroke because there's more fluid load, and you're losing more of your surface stroke lost to stretch. Okay, and now let's look real quick at this number here. If the fluid load divided by the stroke length and spring constant should be going down as we raise the fluid level. So here's 0.27, 0.253, losing less of our surface stroke to stretch, 0.216, and that's what that F over SKR represents, the decimal fraction of your surface stroke lost to stretch to pick up the fluid load. All right, so let's go look at this example. So if I click on my Windows Explorer, and I have some files that we've downloaded from the web page, and the PDF file that Carrie Ann's put together on the web page on Ask Echometer. And these are two examples that we're going to import and overlay on top of the predicted data. And this is the one we just talked about, fluid load as a function of pump intake pressure. And it has an extension of QRod, and QRod recognizes that extension. So I'm going to double click on fluid load as a function of pump intake pressure. And you have to accept the terms and conditions. You say accept. And then when QRod opens up, it's a software supported program by advertisements. And so an Echometer advertisement runs and says buy model H, intrinsically safe model H. When you click, but this is the input data that we just loaded in. We say calculate. And this is the calculations here with 500 psi pump intake pressure, and I guess this has the smallest. You probably can't hardly read this. FO over SKR, 21%. And if I go down to 400 psi and say calculate, then that's going to go to 0.228. Only 22.8% of the strokes lost to stretch. And again, the pump card's getting higher and the stroke length's getting shorter. And as we make these changes, we can see the impact, 300 pounds, and say calculate. We see that the stroke length's getting shorter. We're losing more of our stroke to stretch. And so QRod's a wonderful what-if program. You can say what if this or what if that, and make a change and see how. We'll talk about that during the class. All right, so now I'm going to get back to our presentation here. And we're going to talk about over travel and under travel. Now, when you pump very, very slow, then the surface stroke and the pump stroke are related. And the surface stroke, the pump stroke is shorter than the surface stroke by F over SKR, and that's all that changes the pump stroke length is just a stretch. But as you pump faster, the dynamics of the system cause the pump stroke to lengthen, get longer. We call that over travel. Now, when you talk about a pump card that has over travel, though, it has too much over travel. Or a pump card that has too much under travel usually has too much under travel. But basically, the idea of under travel is a pump card that has lots of wide stretch, and over travel card is one that has a pumping speed faster than 0, which is starting to get some additional pump stroke due to the inertia of the pumping system causing the pump card to have a longer downhole stroke than just the stroke due to the surface stroke minus the stretch. So this says that when the pump stroke moves less than the polished rod stroke, it's an under travel card. Those cards often are in the field due to stuck pumps. The plunger's too big for the rod string may be too small. Have sand or scale causing extra friction. Over tight stuffing box or extra mechanical friction. So all those things can create an under travel card, which means more stretch. And then the under travel card, but the over travel card usually is pumping faster or having rods that, like fiberglass rods, stretch a lot, and they can be an over travel card. Great one. So this is an example in both in TAM and QRod. This is predicted in QRod, and it's the under travel no anchor QRod file, and this is the under travel TAM file. And so if we go into TAM and look at this data, well, first of all, let's just talk about it. We can see here that this surface load is almost all stretch. Okay, so this slope right here is all stretch. This is stretch and then unstretch. And so we're losing our pump stroke due to stretch when the surface card looks like a a plot of loads that go up and to the right. When the loads go up and to the right, then the surface stroke is being lost to stretch. And so this surface stroke is measured, plotting up and to the right. That means there's a lot of stretch. So when you see a surface card look like this, that's sloped up and to the right, parallel to the spring constant of the rod spring, Kr, then you should think, my gosh, this well has a lot of stretch. Why? Well, you don't know why, but maybe it's because the rod string's too stretchy, a lot of mechanical friction, the pump is really big. That's what is causing the pump card to have a short stroke. And so in this well, the surface stroke is 45 inches, and the pump stroke, effective pump stroke, is only about 18.6 inches. So if we go into our TAM software, let's go into our TAM software, and I think it's right there. Yay. And if I'm going to go to full screen, and I go pick a well, and the well I'm going to pick is the under travel card inside of the QRod folder. So from all these different Ask Echometer online presentations we've done, we've had many different examples that we put out that accompany the presentations. And so each of those examples get installed into the Echometer online folder. In most of the cases, the ones I presented do. And so QRod is in this same folder. And so we're going to look at this under travel example. And so we're looking at the dynamometer card, and this is a valve test that they did. And we're going to click on this tab, and here's our under travel surface card and pump card. Again, notice how this surface card's slope is along the line of the tubing stretch line and the KR line, and it's sloping upward and to the right. That means it's all the surface strokes being lost to stretch, and we have a very short downhole pump stroke. If we right click on the surface card with our mouse, then there's an option here to export the surface stroke, this is stroke number 5, to a dyne file. When we click on that button, then we have a file that's created called under travel dyne, and it gives us a date and time, and we can see that the extension is dyne right there. You can see dyne, and so that file right there, QRod will read in and overlay the predicted surface card. So if I go find this under travel file that I created in the past, and I double click on it, then that opens a new advertisement. This is the wireless equipment. And if I click calculate, then this is the data that QRod calculates based on the same inputs as what are in TWM in the background. Okay, so we have the same inputs, the same pump intake pressure, the same rod string. Well, it's a 7/6 rod string. It may not be exactly the same because the operator may not have ran the exact same API taper that was 34% 7/8 and 66% 3/4, but it's close. And so when we import the dyne file and overlay it, it should match up really close. So we're going to go to Tools and Overlay Dyne File, and we see I've already looked in this folder. So this is 2020 September the 30th Ask Echometer presentation. And so when I click on the under travel dyne file and I say open it, then you can see that there's a very good match between the blue curve and the ugly pink curve, fuchsia color. But look, there's some extra mechanical friction because the QRod loads are going higher on the upstroke, but they match really good on the rest of the card. Really good match. Almost identical. Okay, now what's going on here? So if we go back and look at the TAM program, what we see is that there's extra mechanical friction here on the upstroke above the maximum load, and that's what's causing this extra load here on your measured diagnostic data. Okay, what is this source? Well, maybe there's a deviation, some kind of mechanical friction, maybe there's paraffin. I don't know. This is some old data that we had from back in 2004. All right, so I'm going to go back and I'm going to open QRod back up, and I'm going to close it back out and start over again and go into TAM and pick the over travel card here in TAM. And now this well has a CBE test. It was done in 2002. And it has a valve test, and here's our dynamometer test, and we're looking at stroke number 79 in TAM. And this rod string, if I click on this little picture here, has 7/8, 3/4, and 250 foot of weight bars. And so let me cancel out of that and go back to my file viewer, and I'm going to find the over travel card and double click on that and say calculate. And now look, we've got a similar shaped card, and we've got a much longer over pump stroke than the surface stroke. The surface stroke here is what is it, 70, EPT is 78.9, and up here we're saying the pump stroke is 76, so it's a little bit shorter. And if we go to Tools Overlay, and go to the over travel card that we exported, and say Open, then there's still a pretty good match, but again, there's little differences in the two, but it's still not a bad match. All right, so let's go back to our presentation. All right, so here's this presentation we just talked about under travel, and here's the same over travel data we just looked at. And this is a well that has a steel rod string in it that's going 14 strokes a minute. And so this is a little bit unusual for a steel rod string to be going so fast. Normally it'd be a fiberglass rod string, would have a lot of over travel, but this well has 31 inches of increased downhole stroke due to pumping 13.74 strokes per minute, and the QRod does a fairly good job of modeling this well. Now, why would I talk about over travel and under travel? Because a long time ago we found that when you operate a well with severe under travel or severe over travel, you tend to have increased failures. So we tend to not want to have wells that have severe high pumping speeds or large amounts of surface stroke loss to stretch, because that tends to have an increase in failure rate. So you need to try to stay away from those and design your dynamometer cards to fit out here in the middle of this group. All right, so this is still a bit more on the over travel, under travel idea. And QRod lets you design a well that has 0 strokes per minute. Now, there's no such thing as 0 strokes per minute, because that means it stopped. There's no motion. But if you could move at 0 speed and you would have no dynamics, then this would be your surface dynamometer card, which would be the weight of rods and fluid here, and this would be the rod stretch. It's anchored. This would be the weight of rods and fluid plus your pump load, and then this would be the weight of, this would be your rod unstretch, and then this would be your synthetic pump card, and you would have 27% of your surface stroke loss to stretch. Now, what happens when you, but look, there's no over travel. 0 over travel at 0 strokes per minute. As you increase the pumping speed, what happens? Well, what happens, this is a video, and so I'm starting to increase the pumping speed. I'm going to go and go faster and faster. And as I increase the pumping speed, notice that this pump stroke is getting longer and longer and longer. We're starting to see acceleration forces on the upstroke and downstroke. So you no longer have a flat low line on the up and a flat low line on the down. You start to have acceleration forces, and you start to have increased downhole stroke. All right, now here is the stroke I stopped at, 11 strokes a minute. In this case, you can see that we have the same amount of stretch lost due to the fluid load. The fluid load stays the same, but now this example has 13.8 inches of over travel. Now, before we had just the weighted rods and fluid plus the pump load on the upstroke, and now we have additional acceleration force of the fluid load plus acceleration force of F1. So F1 is 11,378 pounds, and then F2 is the force that drops below weighted rods and fluid, and that's 4,100 pounds. And so there's a dynamic change in the surface card and pump card as the speed increases, and the result is that you get additional downhole stroke due to over travel. You have additional peak load on the upstroke and a lower minimum load on the downstroke, and higher horsepower as you pump faster. Now, this is some data that we collected on the Texas Tech test well. And we were able to control the speed with the variable speed drive and control the angular rotation of the crank so that it was constant. And so this is starting out. We acquired data with the horseshoe load cell, and the plunger clearance was 5 thousandths between the plunger and the barrel. So the pump clearance was 5 thousandths of an inch. It was a 7/6 rod string. Pump intake pressure is about 135 psi. We shot fluidables to determine that. And the surface stroke length was 105.6 inches long. Now, one stroke a minute, even though the tubing was anchored, the pump is not a rectangle like the synthetic card that we would predict in QRod. The reason why it's not a rectangle is because on the upstroke there's a lot of slippage because the plunger velocity is so slow. And so the pump card starts to move to the right when you're picking up the fluid load at slow velocity, and you lose efficiency due to slippage. And so this motion, this displacement here of about 10 inches is due to lost downhill stroke due to the liquid above the plunger slipping through the gap between the plunger and the barrel, causing the plunger to move up, slippage. So here the maximum plunger travel to right there was 98.97 inches, but note that the pump car is not a rectangle. Now we increase the pumping speed to 2.5 strokes a minute. Notice now that there's less slippage. Why? Because the plunger velocity creates turbulence between the plunger and the barrel and reduces the amount of slippage when we pick up the fluid load. So this line is becoming more vertical. We're starting to see a little bit of peak load and minimum loads. Now let's go back here and look. Look, there's almost a constant load on the upstroke. That's the weighted rods and fluid plus the pump load. And as we increase the speed, we get an acceleration, and we start to see a peak load due to acceleration picking up the fluid load on the upstroke, and a peak load due to releasing the fluid load on the downstroke. And then this peak is the echo of that up and down the rod string, and that's another echo and echo and echo and echo, and these are echoes on the downstroke of these minimum loads and peak loads based on the acoustic velocity of the rod string. That peak load bounces up and down the rod string. And there's 5.06 strokes a minute. Now look, if we go back here and count this, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 echoes. And now that we're going faster, there's less time, so there's 1, 2, 3, 4, 5 echoes, half as many as we go faster, half as much time for it to repeat. And now we're getting a bit longer stroke. Not much, about the same stroke length. And then here we get 99.6 at 7 strokes per minute and 4 echoes. And now we get maybe 3 plus a little bit on at 8.26 strokes per minute. We get a little bit longer downhill stroke. And then here at 9.64 strokes per minute, we get even longer stroke due to over travel. And we have a higher peak load, lower minimum load, and again we're having an increase in horsepower a little bit. So horsepower, 8.4, 6.9, 5.7. As we pump slower, the horsepower is going down. Anyway, and that's the overall comparison of all strokes over lane. And you can see the color here identifies the stroke, and the slippage. You can see as you increase the speed, this line becomes more and more vertical, and the fastest one has the most vertical. Even though it's still leaking a little bit, the faster velocity you have a little bit less slippage. It's a shorter time also. Plunger velocity. This is a plunger velocity for 1 stroke a minute, and right there is where the standing valve popped off the seat. The velocity plunger is high enough to open the trailing valve. Here is the same stroke length, 100 inches, about 100 inches, a little bit different velocity profile than pumping really slow. And if you compare them, you can see that this velocity profile, pumping 9.6 strokes a minute, is much different than pumping 1 stroke a minute. But the valve, if you pump slow enough, the valve wouldn't even open. But here, pumping 1 stroke a minute is fast enough to open the standing valve on the upstroke. All right. We designed a rod string. We designed the rod string based on. In fact, I'm wondering if we should. Are there any questions, Gustavo? We might want to take a couple questions, because I'm just going to work through this presentation, and we may not have very much time at the end of the presentation to ask questions.
Yes, we do have some questions, Lynn. There's a first question from Travis. His slide number 11, when you were checking one of the slides on the main windows, QRod asking for, does the NEMA D motor size apply to gas engines?
Geez, gas engines probably have more slip, so I'd say that a gas engine is probably like a NEMA D motor, because it's has that big flywheel typically. It slows down at the peak torque. You know, the NEMA B motor that really isn't designed for cyclic loading tends to be stiffer and not slow down. And so when you use a NEMA B motor on a rod pump system, you tend to get higher current draw, and you'll have to use at least 1 to 2 sizes larger motor than what QRod will predict. An NEMA D motor slows down when you have the crank arm at 90 or 270 when the torque is high, and that reduces the current flow and it prevents thermal loading of the motor. So yeah, it probably would be reasonable for a gas engine.
Okay, another question is kind of a common one, asking which one is better to use, clockwise or counterclockwise, and why?
It's better to be in balance. Now, so to me, it doesn't matter whether it's clockwise or counterclockwise on a conventional unit. If the weights are a certain position clockwise, and why it matters. First of all, a pumping unit, the gearbox shaft center is not directly beneath the tail bearing when the walking beam is horizontal, and so that means there's different crank angles in the upstroke and downstroke, and there's different torque factors, a little bit different. And so what that means is that the torque changes whether you rotate. The counterbalance moment changes whether you rotate clockwise or counterclockwise. So for the current loading, for the current rod position, one method, one rotation, or the other rotation, clockwise or counterclockwise, may give a better in-balance condition for the pumping unit. And so whichever direction rotation puts the least net torque on the gearbox is the best direction of rotation.
Okay.
Now, if you've rotated clockwise forever, and your gears are worn out in that direction, then that may not be a good direction of rotation. So, you know, depending on gearbox wear and damage, there may be a preferred rotation direction for your unit. But normally, if it's in good condition, there's no preferred method the preferred method is the least torque on the gearbox.
Great. Question related to the QRod development. Is there any plan to add a phase beam pumping unit to the unit types?
You know, about every 4 or 5 years we make changes to QRod, and we've been very actively working on TAM and developing new features in TAM. And so I would think that once TAM development gets more complete and all the issues that we have are corrected and most of the features that we want are added, then we may spend, you know, a few months working on QRod again and add some, you know, we need to add a long stroke pump unit like a Rotaflex. We need to have a unit that has a different upstroke and downstroke velocity profile, like a hydraulic pump unit. So yes, there's some things we need to do in QRod.
Okay, one more question is from Tariq about the depth placement of a tubing anchor. Can you tell me what conditions determine the placement? I've been corresponding with him on the chat and talking about sand production and installation of the anchor above the perf, and when you have like thin walls or installing downhole gas separators, you don't want to install it below that arrangement because you may break the downhole assembly. But just go ahead and continue with that.
Okay, so we did a lot of the discussion in the presentation, Ask Echometer presentation that we did on downhole gas separators. So if you have a question about setting a tubing anchor, we talked about that some during the presentation that we previously did on gas separators. So I'd recommend you review that. And then here's the main consideration. The deeper the better, usually for tubing anchors, to keep the tubing in tension to prevent wear. But if you set the tubing anchor below a formation that produces solids, and the solids fall out on the anchor and cause the anchor to stick or block it, then you set the anchor too deep. And so some companies won't set the anchor below their producing formation because they don't want to get solids on the anchor. But some formations don't produce any solids. If you have a vertical well, then it's best to put the anchor deep because you want to set your pump in the rat hole if one's present. So the presentation that the paper that Carrie Ann wrote on tubing anchors can block angular gas flow talks about setting the anchor below the perfs, and there's a good discussion in that paper. So there's a lot of decisions that you have to consider, a lot of things you have to consider when you're talking about running a tubing anchor. If you don't run a tubing anchor and your well is very deep, in a few months you'll cut a hole in your tubing because if you have rod on tubing wear. So anchors are important, especially if the well is deeper than 3,000 feet, or if you run a very large diameter pump. It's important to run a tubing anchor because you don't want your tubing to move and rods to move relative to the tubing and increase rod on tubing wear. All right, so that's my answer.
Yeah. One more question is, you were in slide 24, 25 discussing about the impact of the pumping tape pressure on the horsepower consumption. So why does the horsepower changes from 10.4 to 9.7 when we increase the pumping tape pressure?
When you increase the pump intake pressure, you actually increase the area of the pump card. So the horsepower is this area of the pump card. I don't have it on the screen here, but if you calculate inch pounds, you take the stroke in inches times the fluid load, and this is the biggest horsepower. 74 times 689. Okay, and as you change the intake pressure, the pump card load goes down and the inches change. And so we need to go back and to answer this question, we have to calculate the area of the pump card and see how the pump card area changes, and that's the horsepower. Now, that's what's happening is because as we increase the lift and we increase the fluid load, we're going to increase the amount of work that's being done to pick up the fluid load. and it's going to cause this horsepower to surface to go up. And we should also see a corresponding increase in the area of the pump card. So I would expect that with the highest fluid level, we probably have the least pump card area, which is the least horsepower, and that's the least. We kept the pumping speed 5 strokes a minute, so we didn't change the speed. We just changed the horsepower at the bottom of the well, which increased the peak loads. Now there's more peak loads and lower minimum loads, and more work being done to pick up the fluid from a deeper depth. So there's more work required to lift the fluid as the fluid level goes down. That's hopefully that's the answer. That should be that's the correct answer. I think that's what you see if you calculate it here. I just haven't ever taken the inches times the pounds to get inch-pounds of horsepower at the pump. And that's a good comment. We should do that and calculate pump horsepower and show that the pump horsepower is also changing, but I've just never done that before.
Yes, I think as a summary would be by increasing the pump intake pressure, which means probably one example is having more pumps emergency. The more pumps emergency you have, the more help you have from the well, and the system needs to do less effort or put a less amount of power to lift the fluids.
That's right, because well provides more energy. But that's right. But it should also show up in this area. We should see the area change as pump intake pressure changes. But that's a good answer too. I agree with what you said.
One last thing, and I think is having problems with over travel or under travel. What will be all the possible solutions to fix under or over travel? Assuming that's causing problems for him.
Right. So this slide right here, I've got a better slide that highlights this area and says don't design a rod string here, and I've got one that highlights this area and says don't design a rod string up here. And so why? Well, because these severe over travel and severe under travel cards, by experience, have tended to show a higher failure rate. Now, but I don't have that information on this slide. So the slide, we can send that out to the group. I can send it to Carrie Ann, and we can send it to them and show there's 2 methods that were proposed by. There's a paper we wrote. We wrote a paper. It's on our webpage. It's called Fundamental. I can't remember the name. Parameters, F over SKR parameters and considerations of design of sucker rods, something like that. Norm High and I wrote that because he and I both thought we had the best method to design sucker rods. And what we found was that even though he went short stroke and fast, and I went long stroke and slow, we had the same failure rate, but we had different design methods. And we both tend to design our sucker rods in here, and we had the longest run life, the least number of failures, when we were compared to all the operators out in the Permian Basin, 25,000 wells. So the answer isn't long and slow. The answer isn't short and fast. The answer is maintain a pump filled with liquid, and don't pump way too fast or have too big of pumps or too stretchy of rods, or you're going to have a high failure rate. So you have to have over travel is good, but too much is bad. Okay, and you're going to have under travel because that's just rod stretch. So you have rods that stretch because they're spring, and if you have a fluid load, rods are going to stretch, and that's just what happens. That's not bad. That's just the way it works. So I don't know if I answered the question or not, but I'd recommend you download that paper off our webpage. If you can't find it, email Carrie Ann or myself or anybody else on the email list, and we'll be glad to get back with you and provide more information on that. Okay. Now, is there any more questions, or is that where it start back up?
Well, one question on the private chat was, how does the QRod calculate the total single bar weight?
That's next. It's coming. So what's enough? Yeah. That'll be next.
And the pump friction, does it assume a value?
No, we don't have pump friction in QRod. QRod assumes that there's only friction on the rods as a function of the rod velocity, and that's the damping factor. if you're trying to model extra friction, then at the pump you can put a bigger plunger diameter in, and that'll make more pump load. But you really can't model. There's no place in QRod. TAM has the ability to add stuff and box friction to take out friction that's near the surface, but we haven't put anything in QRod yet to put in point mechanical friction load, so that's not available. Any other questions?
Yes. One more question here is probably a statement that we should do at the beginning of the presentation. The QRod works for vertical wells. And the question is, does QRod serve as a good estimate for pumps that are pumping from the curve in a horizontal well?
And the answer is probably as good as anything else. And so that's not a very good answer, but there's a lot of problems right now with the other programs that are design programs trying to predict the mechanical friction due to deviation and dog legs. And so what I'll usually say is just use a true vertical depth for the rod string depth, and that will work just fine in QRod. But okay, so how are we trying to fix that? So Gustavo and Ken Skinner just went out to a test well near Echometer's office, and we removed the downhole load cell from a well that we're developing with a group called ALRDC. We're developing a downhole load cell to understand how mechanical friction due to dog legs and are applied to the rod string. And once we understand that, we'll be able to build a better model that will model that. So right now the models are not very good because nobody has ever really measured it. It's all just theory, and I don't think it's right. So QRod does just as good as anybody. QRod has matched the other programs just better. QRod matches the best. So I just say use a true vertical depth and you'll probably be fine. All right. Any questions?
Yes. Is there a proper way to adjust a surface card in a tagging condition, considering the stretch effect and the beginning of the upstroke?
When you say tight, what do you mean by that?
A pump tagging down?
No, we don't have you know, the tag is a mechanical force at the end or the beginning of the stroke, and you're tagging because there's a problem. And so the QRod will calculate the downhole stroke length, and it'll calculate the change in the stroke length if you change conditions, but it won't calculate the tag. So I don't know of any program that'll calculate a tag. It'll calculate the change in the downhole stroke length, but it won't calculate a tag. No one does that. So
Julia is having a question that she might need to review another sessions. She's asking, is it possible to estimate the pump intake pressure purely from the dynamometer card in the absence of a fluid level shot? So she doesn't have a fluid level shot. If yes, are there any reference to read about it?
yes,
it's more than that. There's videos. Go ahead.
Yeah. So there's a paper that we have on our webpage that talks about pump intake pressure from fluid levels and dynamometer cards and valve tests. And you know, there's the plunger size is used, the discharge pressure is used, the tubing pressure is used, the tubing fluid grading is used, and so the thing that's not known is what's the tubing fluid gradient, and you can theoretically come up with an estimate if there's no mechanical friction by determining the weight of rods and fluid. So you might be able to get in most cases that won't work because of mechanical friction. But you can if you know your oil and water production rate and estimate the impact based on the gas of the tubing, then you can make an adjustment for your tubing fluid gradient, get a really good close estimate of the pump and discharge pressure, and then based on the height of the pump card, you subtract the height of the pump card from the discharge pressure. The height of the pump card is the fluid load divided by the plunger area, and that gives you the pump intake pressure. And as long as there's not any mechanical friction that you're worried about, then you're going to come up with a very good estimate of the pump intake pressure. So I don't think we've done that presentation yet on the Ask Echometer. As far as I recall, I don't think we've done that.
Yeah, briefly discussions only on the section number 8.
Right. We talked about it in other presentations on how much pump does my pump, and you talked about it in your presentation on how does the dynamometer card features work in TAM. So we've talked about it, but it's not.
And then the reference loads we also mentioned briefly
That's right, reference loads. All right, I think
what
I probably should.
we have so far.
Okay. All right. Well, I'm going to start back up, and then I'll try not to go too fast. But when we design a sucker rod string, the idea behind the design of a sucker rod string is that it's supposed to last for a long time, and it's not supposed to fail due to pulling on the rod string and tension. It's supposed to fail due to wearing out or cyclic loading. And so we design the sucker rod string so the biggest rod's at the top, the smallest rod's at the bottom. It's called a tapered rod string. And when we design the rod string, we try to make the stresses at the top of each taper, each diameter change, equal so that the rod string loading is the maximum amount at the top of each rod string, each rod string taper. Now, there's a method that we use called the modified Goodman method, and that's pretty much accepted in industry. And what we use is this little gray area as the allowable stress range, and you can calculate based on your you can calculate the allowable stress range with this equation. And what we use the tensile strength of the rod string to come up with the calculation. So the T here stands for the tensile strength, and each type of rod has a different tensile strength. And as the rod gets more loaded, then you typically go to a rod that has a higher tensile strength. Now, what industry has found is that this method, this modified Goodman method, tends to force people into using stronger and stronger rods that are called high-strength rods that are more fragile. And so in TWM, we use a service factor of 1, and we don't derate the rods for corrosive environment or salt water. So there's no reduction in the service factor in QRod. But what industry has found that's not in this table, and it's been talked about by the API sucker rod committee, is that they recommend that sucker rod's service factor of 1.25 be used before you go to a higher strength rod. They found that the rods that have a lower peak tensile strength are tougher, and they withstand notch loading or dings or damage much better than the high strength rods that are stronger and more brittle. So you can get a longer run life by using a D grade rod loaded to 125% than a high strength rod, usually in a hostile environment with H2S and salt water being produced. So this is the method we use in QRod called this modified Goodman method. The sinker bar came from experience, and there's a paper that I'm referencing here from the short course in 2007 that Elton Smith was responsible for. And what prior to that time, 1980, Emerald Hess started to use sinker bars, and before they hadn't used. And that's where I worked. I worked for Emerald Hess from 1980 to 2000. And we were having frequent holes in tubing down near the pump. And we started using this design method for sinker bars at Emerald Hess. And all the holes down in the pump due to rod-on tubing wear went away. As soon as we started using sinker bars, it's like a magic. And so I became a big advocate for sinker bars, and Elton Smith worked for Emerald Hess. He went to work for Pioneer, and they adopted running sinker bars, pretty much the same method, maybe a little more than we did, longer length slightly, but their failure rate went from 0.42 failures per year to 2.7 failures per year. And the paper says one of the reasons is because they ran sinker bars. So we put inside, and this just talks about rod-on tubing wear and compressing the gas and causing mechanical rod-on tubing wear to open the trailing valve. And this slide here is a study done by Scott Long. What he did was he said, who is Scott Long? Scott Long sold sinker bars, And if we were ever in a discussion, a meeting with Scott Long, he would always try to say something good about sinker bars. And we always used to tease him about, sinker bars. So he decided to do a test, and he split tubing in half, and he rubbed a small diameter rod with a constant force on the tubing, and it cut through the tubing very fast. And then he rubbed the tubing with a sinker bar, larger diameter, and it cut through the tubing very slow. And Scott found that the larger area of contact reduced the time for the hole to appear in the tubing. And this is a slide that talks about buckling, and buckling is what we think is causing the rod and tubing to come in contact and cause a hole in tubing to occur. And this is I made this slide probably 30 years ago. And what I'm trying to show is that there's different diameters here, and this is a diameter of a weight bar, and this is a diameter of 5/8 inch rod. And if you run a 25-foot long 5/8 inch rod, if you push on the bottom of the 5/8 inch rod with a 25-pound compression force, it's going to buckle and cut a hole in your tubing. So don't do that. Run a bigger diameter rod. But if you run a bigger diameter rod, and let's say it's bigger than 5/8, well, that's 3/4. It just takes 50 pounds. Why, if the little piece of paraffin or asphaltene between the plunger and the barrel creates a 50-pound compression force, well, it'll probably create a 50-pound compression force and buckle your sucker rods. Well, let's run weight bars down there, sinker bars. They're thicker, bigger in diameter, and it takes 50 foot or longer. 200 pounds of compression force causes the sinker bars to buckle. Well, all of the design programs that you pay money for, the default pump friction is 200 pounds. So all that means is that if you run a design program that has a default pump friction, then 200 pounds of pump friction will buckle your sinker rod string. If your sinker rod string is buckled, then it's important that the large diameter of the sinker bar reduces the wear and increases the time for a hole to appear due to rod-on tubing wear. So why did I go through this discussion? Because when you click on the calculate button inside QRod, it calculates a length of sinker bars that works, that has been found by industry to reduce your holes in tubing down near your pump. And so this is the curve that's used, and it's the sinker bar weight equals the pump depth times the tubing fluid gradient times the tubing fluid gradient times the sinker bar factor. And the sinker bar factor is a function of the plunger diameter. So here's the plunger diameter. And so when you click on this little button right here, and this screen comes up, you put your desired length of your diameter of sinker bars in, and it calculates to the nearest 25-foot size that will equal that weight required based on the sinker bar factor. When we click the use in the calculation, it updates that weight right there to that field. And so that's where that comes from. And so that's the background behind the sinker bar calculator. And that's the discussion that's in the paper that we attached to the download file. Okay, that's the answer to how do you calculate sinker bars. Now, the next topic is a slippage calculator, and when there's pressure in the tubing above, this is the plunger, and this is the barrel of your pump, and there's pressure on here that's higher than the pressure below, then fluid is pushed between the plunger and the barrel through the clearances. That's called slippage. Okay, and so this happens when during your upstroke, when the trailing valve ball is on the seat. Now, the pump displacement is reduced due to incomplete pump fillage and pump slippage. And we talked about incomplete pump fillage on session 16. Slippage, we've done a lot of Echometers and been involved in developing the Patterson slippage equation. And slippage occurs when the trailing valve ball is on the seat. So it's on the seat right here. We're picking up the fluid load. And the trailing valve ball is on the seat right here during the upstroke as the plunger moves through the barrel. And then the trailing valve ball is on the seat as you're starting the downstroke to transfer the fluid load from the rods onto the tubing. But slippage doesn't occur on the downstroke when the plunger moves through the barrel on the downstroke because the ball is off the seat, and it's going to prefer, it's not going to be matter because of the pump is open, and there's no issue about slippage. Now, this is a slippage equation, and Echometer went to Texas Tech, probably 40 different trips between 2000. We went to Lubbock, to the Texas Tech University test well, to collect data at the surface to use as reference data to determine this equation. So this equation was paid for by industry. Industry donated over $500,000. Echometer donated equipment and time. Lufkin provided a pumping unit. ABB provided a variable speed drive. And we developed this equation that determines the amount of slippage based on the diameter of the plunger, based on the differential pressure, across the plunger, based on the clearance, it slips more to a power, the clearance, it's reduced based on the length of the plunger, and it's also, the slippage reduced as liquid becomes more viscous, and that's something we'll talk about quite a bit during this presentation. And then this is the other term we added is as the speed increases, the total number of strokes increase, and the total volume of slippage increases as you pump faster. But the weird thing is that the pump becomes more efficient because the velocity of the plunger increases and the percent of stroke lost, slippage per stroke, goes down. So you get more strokes per day, more slippage, but you get less volume per stroke lost due to slippage. All right, so this is the equation that we were involved with developing. We call it the Patterson pump slippage equation. Now, I was involved with the research a lot, and so I'm listed as one of the co-authors on this paper. And John Patterson was a primary author. Kyle Chambliss was second author, and Kyle he works for Oxy. He got a PhD at Texas Tech during this research. Myself and then Jim Curfew. Now we discussed whether there should be this table or not in the paper, and Echometer advocated that we shouldn't put a table and tell people what clearance to use. We should just use this equation and say use this equation, the Patterson slippage equation. So we were democratic. We voted, and the vote was to put the table in the paper. And so for the Permian Basin, for 8,000 foot less depth of well, 4-foot plunger, 1.5-inch pump, use 5,000 as clearance, inch and a quarter use 5,000 clearance, 1.5-inch use 6,000 clearance, 1 3/4 use 7,000 clearance, 2-inch pump diameter use 8,000 clearance, and then 2 1/4 pump use 9,000 clearance. So this is one of the recommendations in the paper, and there wasn't a lot of agreement on it, but we did discuss it, and we decided to put this in the paper in 2007. So in 2012, I wrote a paper said don't do this. Okay, and it wasn't because I didn't like these guys. They were really good friends. I have a lot of respect for them. The reason why I wrote the paper was because of this table right here and what this table shows. And what I was getting a lot of feedback from customers was that the pumps are leaking too much. And so if you put a 1 1/4 pump 8,000 foot deep, here's the spreadsheet that's that you can download from our webpage, and you put in the plunger diameter and the clearances and the fluid viscosity and the strokes per minute and the plunger length, then you can calculate based on that table how much slippage you'd have. And if you notice here, if you're 1.25 inch pump, your slippage is 37 barrels a day, and for a 100-inch stroke, your pump displacement is 131, and you're losing 29% of your pump displacement to slippage. That's quite a bit. But if you look at 2.25 pump with 9 thousandths clearance, you're losing 79% of the pump stroke to slippage, which is excessive. And so that's why you should use this equation to calculate and size your pump clearances, and not size your pump clearances based on the table. All right, so that's there. Now here is some of the research that we got from the Texas Tech test well research. Is that this plot right here shows that as you pump slower, the amount of the pump displacement loss to slippage increases. So look, if you were pumping about 1 stroke a minute, then you would only get 15% of your pump stroke to surface, and you lose 85%. 85% of what you'd lose due to slippage. If you pumped about 0.6 strokes a minute, 0.6 strokes a minute is about right there, then all of your pump stroke would be lost to slippage. So if you had a 9 thousandths pump clearance, so it depends on your pump clearance, but it depends on your pumping speed. So as you pump slower, your efficiency of your pump due to slippage goes way down. But if you look here, as you pump faster, from 4 to 10 strokes a minute, the pump efficiency, the amount of pump displacement produced to the surface, is between 80 and 90%, which is what you'd want. You wouldn't be losing more than about 10%. So what this is saying, that the pumping speed has a big impact on the efficiency of the pump. As you pump slower, you lose more and more of this pump displacement, pump stroke, to slippage. Now this is an example of one of the tests that we did, and this is a test well. We had 5 thousandths clearance, and the pump efficiency was 80%, 80 to 88% measured. It was slipping 21.4 barrels per day. The speed was 7.4 strokes per minute. Had 5 thousandths clearance, 1.5 inch pump, 7/6 rod string, and this is the TWM measured data, surface card and calculated pump card, and this is the predicted data, which is a really good match. And if you go into QRod and we overlay the card, you can see that they match really close. And in QRod, you can say compare, and this little table pops up and shows a comparison, and you can see that the peak load was within 2%, and the minute stroke length was the same, and the horsepower was within 3%. And again, notice that the minimum load was off by about 10%, but again, I think that's because we had possibly different damping factors on the upstroke and downstroke, possibly. That's probably the main difference. A little bit different friction on upstroke and down. So the slippage tool is right here. This is a button in QRod, and you click that button, then this screen pops open, and all these inputs at the top are already typed into QRod. And now you need to type in the pump clearance and the fluid viscosity. And what's fluid viscosity? Well, I thought it was 1 for water. It's actually less than 1 when the water is warm. And the Texas Tech test well was 4,000 foot deep. And this is the viscosity for the water in the Texas Tech test well. And that's the default. And then this is the plunger length. And so when you click calculate, you then go calculate your pumping speed, and it calculates your surface and pump card. And then we calculate the efficiency, which is 89 versus 88.2, or 90 versus 88.2, which is really very close. So QRod calculates your slippage based on your pump card and your pumping speed. And it also shows this table, a plot. I guess it's a plot, not a table. And it shows you along the bottom here axis is pump clearance. And we want a certain amount of pump clearance in this well. based on our input data, and then we need to know that this is how much slippage we'll lose. And so this well, we're going to lose about 19 barrels a day of pump displacement due to slippage if we run a 5,000 clearance. If we run a 4,000 clearance, then we're going to lose about 15 barrels a day. If we run a 9,000 clearance, we're going to lose about 40 barrels a day. So you, as an operator, need to decide how much slippage you want. Now the question often is, well, how much clearance do I need? If you ask the pump manufacturers, they'll say you need slippage for pump lubrication to prevent galling. And how much do you need? Well, you need between 2 to 5% of slippage to prevent galling of the plunger to the barrel. Well, this is about 10% with 5,000 clearance. To get down to 5%, you need 3,000 clearance. So out in West Texas and around Wichita Falls and other places, it's the common old practice was to use 3,000 clearance, which would have been about 5% slippage. Now, why is slippage important? Because most of the knowledge before we did the Texas Tech slippage test was that if you ran 7 or 8 or 9,000 pump clearance, you would lose all your pump displacement to slippage to the clearances, and so people tended to not to open their pump clearances up. And so when you click, so this is a Texas Tech example well, and when you click calculate based on the measured versus calculated, we calculate 159, we measured 160, we measured 159, we predicted 164, and we calculated very close to the same pump slippage as we measure the Texas Tech test well. So this was the QRod works is pretty darn accurate. Now, so what's our recommendation? Our recommendation is use QRod and assume it assumes 100% pump fillage, and then use a calculator and adjust the viscosity for the temperature at the pump, and then use the plot of the Patterson slippage equation to select the pump clearance. And that's what our recommendation is. Now, here's a well that caused me to realize that the table was a bad idea. And so this operator was running this well at 9.52 strokes a minute, and he ran, it's a 2 1/4 pump, so the plunger diameter is 2 1/4 with 9,000 clearance, and he had collected the data and he texted me or emailed me and said, where's my production? What's wrong with my well? And so the program calculates that there's 155 barrels a day slippage based on the conditions of his well. And if he ran a 5,000 pump clearance, then he would be leaking about 10%, 65 barrels per day slippage compared to 655 barrels of pump displacement. But instead, he ran 9,000 clearance from the table, and he was getting about 160 barrels of pump displacement that was lost. Okay, and so where was his production? Well, we'll talk about that a little bit more in just a minute. So here's the effect of viscosity. Now, if you have T3 is 120 degrees, T2 is 85 degrees, and T1 is 250. So if you have only water viscosity gets much less than 0.76 at hotter and hotter temperatures. So water viscosity, if that's the only viscosity, it's going to the viscosity can be very, very low. And here is the data that we measured as slippage in barrels per day versus pumping speed. And you can see as we pump faster, we got more total barrels of pump slippage. And if we corrected it for viscosity with the 0.76 viscosity, we got a really good match, and so that was our default in 2007. And here is our slippage calculation for this well with 0.76 and 155 barrels a day with the Patterson slippage equation for that well. And here's his data. Now this data was shown in a previous presentation, and it's in your folder called Liquid Pumps, and it's the 6th session in Ask Echometer on pump clearance. And so the operator acquired this data at the well, and his question was, why am I only getting 402 barrels a day at the surface when this pump displacement should be 577 barrels a day? Now, I asked him, I said, what's your pump clearance? And what do you think he said? He said, I don't know. I said, well, why don't you know? He said, because someone else decides the pump clearance, not me. And I said, well, it might be your pump clearance that's causing you to lose that 160 barrels a day of pump displacement. And so he called me. I said, you need to find that out. So he said, well, how do I find it out? I said, you go to the pump shop and see who signed the ticket, and you call that person and ask him, how did he decide what pump clearance to use? And so after he spent 2 weeks trying to find out who set the pump clearance. He talked to a guy on the 50th floor in a building in a big city, and that guy said, well, I read that paper that Lynn Rowland wrote that said that use 9,000 clearance for a 2 1/4 pump. And I said, don't do that. Use a slippage equation. So anyway, this says that they lost all the pump displacement due to slippage, and the pump was about 70% efficient. And so in TAM, we calculate the correction for pump displacement, and TAM calculates a good match. We calculate 404 barrels a day versus at stock tank versus 402 that they measured using a 0.76 viscosity, and that's a good match. But this is a well up in Wyoming, and the operator said, hey, you're way off. You're calculating a lot of extra slippage on my well, and I'm not seeing that that much slippage. I'm getting a lot more. And let's see what let's go here. So if we use a 0.76 viscosity, we get 391 barrels a day, and that means that there's too much slippage. And what we found that if the API gravity of the oil is less than 30 to 32 degrees, we need to use the oil viscosity or a mixture for the pump well, we should use just oil viscosity for less than 30 degrees API gravity. And so there's using 0.76 doesn't work when you have a heavier crude. Here we used the oil viscosity 2.539, and we matched up within 2 barrels per day. So viscosity is an important number in the slippage equation, and it works okay when the oil is light, but when the oil is heavier, you need to use a different viscosity than 0.76. This is just showing the information about that pump, and this is a spreadsheet that's on the download file that lets you calculate the viscosity of the fluid for your well based on the API gravity. So you can use this spreadsheet to come up with the viscosity of your produced fluids. So you input the oil and the water production, you input the API gravity, the gas gravity, the reservoir temperature, the bubble point pressure, you use the bubble point pressure of your intake pump intake pressure, and then it calculates the average viscosity for your oil between your intake pressure and your discharge pressure, and that's the pressure, that's the viscosity you should use for your slippage calculations if your oil API gravity is less than 30 to 32. And it's just showing here that inside the TAM software, when we use the correct viscosity of 2.5, then we get a good match on our measured versus calculated. So you can use this technique to match what's going into the pump. You can use it to estimate your pump wear. You can adjust the pump clearances to see when your calculated pump displacement matches what's going in the tank, and that would show you about how much wear your pump has had. You can use it to estimate how much remaining life you may have. You can use it to estimate your performance of every well by using QRod and adjusting your pump clearance to see how much wear you've had in your well. So why did John Patterson and Jim Curfew want to open up the clearances with that table? They had found that they had a lot of problems with sand, and so they were having a lot of wells with plungers that were scored, looked like this. And so their recommendation was, if you have plungers that are being scored, open your clearances up and let the solids pass through between the plunger and the barrel, and pump more strokes, but have less damage to your plunger and your barrel. So but you got to design your pump displacement to overcome the slippage. So this is why they wanted to have more open clearances, because with the tight clearances that they had been using in the past, they encounter a lot more damage to their pump, plungers, and barrels due to solids. So if you have mostly water, 0.76 is a good guess. If you produce oil with a gravity less than 32, then you may want to use the oil viscosity below 32, and then use the total fluid viscosity, oil plus water percent, if it's greater than 32. Use the average pressure of your pump discharge pressure and your discharge pressure. Use the temperature at the pump. You have to know your plunger length, your diameter of your pump, and your clearance. Clearance is sometimes hard to come up with. This is a lot of data to calculate this. You need to know your oil, water, and gas gravities. And then you should use your bubble point based on your pump intake pressure to determine how much gas is in solution. You need to get a representative card if you're trying to match production. It's sometimes difficult to find the data. That makes it hard sometimes to find your pump clearances if you're not involved in that loop. It helps you be able to calculate how much liquid's in the tank based on slippage. 0.76 worked pretty well until we started coming into wells that had heavier crude. Use the oil viscosity when the API gravity is less than 32, and then use the total fluid when it's above 32. The weird thing about the slippage test that we found was that as you pump faster, you get more total barrels, but as you pump faster, you lose less percent of each stroke due to slippage. Interesting. The Patterson slippage equation is a lot better than using a rule of thumb. Slippage impacts efficiency of your pumping system. It reduces your pump displacement because of slippage. You have to put in more power. You need some slippage for lubrication, and you may want to consider more open clearances to pass solids. So all those are important. It's a function of speed. As you pump slower, you get more slippage. If you have a leaky, worn-out pump, you can pump faster and get more production out of the well because the velocity creates turbulence. If you have large clearances and the well's deep with high differential pressure and a low pump intake pressure, then you can have a lot of slippage. You need to correct for the temperature, and you need some slippage in your well to provide lubrication. Carry on, it's getting close to 2 o'clock. I mean, time to stop, isn't it? I've got a few more slides. Should I keep on going?
Sure. Yeah, keep on going and finish that. That's
Okay.
perfectly fine.
This example is a hole in tubing. And this is what the data looks like in TWM or TAM. And the pump card is not very tall. And this data is acquired with the PRT. Now, if you put the same conditions in QRod and calculate it, QRod doesn't calculate a hole in the tubing. QRod calculates what the load should be. And QRod says, hey, the loads on the upstroke, peak load should be 16,500. And look, the peak loads are way too low, but the minimum load matches up. So on the downstroke, the pump card is going to be okay. On the upstroke, we're missing some of our load. And the pump card is not tall enough. And here, look, the pump card is 2,400. It's supposed to be 3,000 pounds tall about, and it's about half of that. So this is an example where you can use QRod to compare what you measure to say, hey, there's a big discrepancy between what I'm measuring and what I'm calculating. And I'm missing about half of my pump load. And so this is an example of using QRod to troubleshoot your well. This next few slides are for Gassy Wells. This is a well that the operator slowed down and took off the anchor. It was 9,000 foot deep. It had a 64-inch stroke, an 1.5 inch pump. And he was pumping 12 strokes a minute. And he was making 50 barrels of liquid to the surface. And the pump stroke calculates 150 barrels a day. So the pump was probably about a third full, because only a third of the pump displacement made it to the surface. So he was pumped off. So he had a high failure rate because his pump wasn't full, and he was pumping 12 strokes a minute. And so he decided to slow this pumping speed down and take off the anchor, and that's the name of the file, QRod file. And so here's the conditions when he was pumping at 12 strokes a minute with the anchor tubing. He was having trouble getting the anchor to hold and set. And so he said, well, I'm going to fix this. I'm going to slow this well down and take the anchor off when I have the next failure. I'm tired of all these failures. But think about this, 50 barrels a day, the pump was less than a third of the stroke full. So he was way pumped off. He was over pumping the well. So he's going to slow it down from 9 to 9 strokes a minute. So when I slowed it down, now, why did I find out about this? Because the operator called me and said, we took out our tubing anchor and we slowed it down to 9 strokes a minute, and we're getting nothing, no production of surface. And I said, well, let's just put this into QRod and see what QRod calculates. When I got down to 9.8 strokes a minute, I said, cuss. I said, there's no downhole stroke. You've ran a pump in your well that all of your surface stroke has lost to stretch and tubing movement. And he said, what should I do? And I said, well, you shouldn't have done what you did. And so all he would have had to have done here is just change the plunger size to 1.25 inches, and he would have got the production that he needed to make, and he would have been okay. But he didn't do that. So the answer was, run QRod one more time, change this to 1.25 inches, and see that you can make about 154 barrels a day with a pump that's almost full at 9 strokes a minute, but you can't with a fluid load from an 1.5 inch pump. And so this is just an example of using QRod to identify what's wrong with my well. Now the last few slides here are on Gassy Wells, and we talk about a gas well or really gassy well. The wells have problems with liquid loading, and so you can produce wells that are liquid loaded with a rod pump well very efficiently if you can set your pump below the kickoff point, below the inner rat hole in a vertical well, and pump the well and just pump the liquid up the tubing and let the gas flow up the casing. Now, it doesn't take much horsepower to pump only a few barrels a day. So this is an example of running QRod, and we're pumping 34 barrels a day with a 5/8 inch sucker rod string with a inch diameter pump with a 5 horsepower motor from 9,000 foot. Okay, so what does that mean? That means that you can pump from 12,000 foot deep up to 20 to 30 barrels a day from a deep depth and not overload a little tiny gearbox. So you can pump from really deep depth with a light rod string and a small diameter pump, and produce it with a low horsepower pump. So don't forget that sucker rod lift is an economic and effective method to produce and dewater wells, gas wells, when there's not much liquid to produce. You have a little bitty pump unit, little bitty rods, little bitty pump. So, QRod, the price is right. It's free. You can download it from the Echometer webpage for no charge. You can use it. It's very accurate. It's very simple. It lets you use English or Spanish to display input and output. You can use any system of units, so it could be used any place in the entire world. It simplifies the input. It keeps you out of all the complicated details. It's very accurate. It uses a damped wave equation. It calculates torque, pump capacity with very little input. It's a lot better than guessing for sure. That guy that pulled his tubing anchor out and slowed the speed down, it would take him about a minute to find out that wouldn't work. QRod would have been a free and easy solution to check that before he did it. It calculates very accurate pump slippage and pump clearances sizing. It's a good tool to use to size your pump clearance. And it's kind of neat. You can overlay a measured surface card and a predicted card and see a match. So I think that might be the incorrect link. I'm not sure I fixed that link right there. Okay, that's it, Carrie Ann. I've exceeded my time.
All right. Well, thank you, Lynn. Do we have any more questions? Do you want to address any?
We have just 2 questions left. If you want to go through it,
Yeah,
Lynn.
that'd be fine.
On the QRod results, we have questions. Well, only one question actually. It is related to how is the static stretch calculated? He thinks it looks like, I think he's right. The FO, which is the fluid loads, over the SKR is the ratio between static stretch and the surface stroke length. But how is the static stretch calculated?
So when you look at QRod and you specify the API rod taper and you specify the pump depth, okay, then that becomes a giant spring. Okay, and the spring has a spring constant, F equals Kx. K is the spring constant for the rod. So if you change the depth, so this rod string that's 7,054 foot long has a spring constant of 175 pounds. If I make this rod string shorter, then it's going to become stiffer and harder to stretch because, let's make it 5,000 feet. Okay, 5,000 feet, and say calculate. See, the spring constant increased because now it's stiffer. It's not as long and stretchy. So the amount of surface, and it doesn't match up anymore. But I guess my point is that if you take the fluid load divided by the surface stroke length here is 72 inches times the spring constant. That's this number right here. If you divide that into your fluid load is right there. So the amount of surface stroke lost to stretch is the fluid load divided by SKR, that number right there. So every time whenever you change the rod string, the pump size, the rod string length, whether it's steel or fiberglass, QRod automatically recalculates the spring constant for the stretch. So is that the answer that you agree with based on the question, Gustavo?
I'm not sure if I was asking about that or asking actually how the static stretch is calculated. But yeah.
The static stretch, this number right here,
yeah,
is the surface stroke times F over SKR.
Yeah.
You want,
okay.
So that's a simple answer. Thanks.
Okay, Travis is having problems. He's asking, well, he has a lot of wells that only makes 5 to 10 barrels a day, but it's impossible to get the pump capacity that low due to their pumping unit size. So I'm assuming he has a large stroke length in those units. Since we do not have electricity for a pump off controller, how can we get good pump failage?
Okay. You have to change the stroke length so it's short. You have to change the plunger size so it's small in diameter. Or since you're on gas and you don't care about your gas bill, you can run a variable slippage pump from Harvest & Fisher that leaks, and you can fill your pump up on the downstroke with slippage, and at the top of the stroke the pump will be full because if you space out the variable slippage pump out at the top of the stroke, the tubing fluid will fill back up the pump and it'll be full every stroke. And so that means that if you do everything you can do to reduce the pump displacement, it's still too much, then put a leaky pump in, the Harvest & Fisher variable slippage pump, and the pump will be full and you won't compress any gas or liquid, pound fluid, on the downstroke, and that'll increase your run life. So that would be my recommendation. If you do everything you can do to minimize your pump displacement and it's still too much pump displacement, and you can't control runtime because you've got a gas engine, then run a variable slippage pump. And there have been companies that have done that and it has worked. And so that is something that people have done. So it's not just it's just not a crazy idea.
Yes, I'm replying to Travis to the specific pump name so he can track it. I'm assuming he already had the smallest stroke length, the smallest pump plunger diameter he can have, and the smallest pulley size, motor size.
Okay, so
more pulley size.
So on his problem wells, I mean, you can run a jack shaft, and that's like $3,000 or $4,000 or $5,000. That's expensive. You could just run a variable slippage pump, and that's about the same cost. And so pick your problem wells. Pick out 3 or 4 problem wells that have high failure rates. Run the variable slippage pump in those wells and see if that doesn't stop them from failing. And then if that works, then you might want to expand it in your field. So do a pilot project, try out 4 or 5 wells and see what happens. And if your wells are failing like every 3 or 4 months, you'll know pretty darn quick that it works because it'll stop those compression failures.
Well, that's all we have.
All right. Thank you guys very much.
All right. Well, thank you, Lynn, and thank you, Gustavo. And thank you all for joining us and for the great questions and comments. In the event you have any follow-up questions, we always welcome your calls and emails, so please do reach out to us. We will keep you informed about the session that's coming up next. We try to get notifications out on LinkedIn, and we'll send out an email, but I will send out an email when this session is ready to view on our YouTube channel. So we really appreciate you guys joining us today and hanging around, and we hope to see you again soon. You have a wonderful afternoon and a great weekend. Thank you all.
Bye.
See you all later.